Hello, it's Milad here, and today I'm going to talk to you about the Central Limit Theorem. Central Limit Theorem, or CLT for short, is a fundamental and significant part of probability theory and statistics. In this video, we will first highlight some of the consequences of Central Limit Theorem, then we will look at some of the assumptions and conditions that we need to consider before applying the CLT. In statistics, we often avoid studying populations, mainly because examining populations is time-consuming, difficult, and in general, very expensive. To avoid doing that, we take samples, which are a small portion of populations, and study them instead. If the samples we take represent the population well, we can extend the statistical analysis of the sample to the whole population. The Central Limit Theorem can help us establish a relationship between mean of a population and means of the samples that were taken from that population. For instance, in this diagram, the CLT can help us establish a relationship between mu, which is mean of the population, and x bar 1, x bar 2, and so on, which are means of the samples that were taken from this population. Here is the Central Limit Theorem in simple English. Given any population, for example this one, if you repeatedly take samples of a specific size, for example size n, from this population, all sample means, or x bars, will have a pattern that closely resembles the shape of the normal distribution. Furthermore, the mean of all sample means, or mu subscript x bar, will be the same as the mean of the population mu. And lastly, the standard deviation of all sample means, or sigma subscript x bar, will be the same as the standard deviation of the population, sigma, divided by the square root of the sample size, n. Knowing how the mean and standard deviation of sample means are related to the mean and standard deviation of a population, we can come up with a standardization formula similar to this. This formula could be used to calculate the probability of seeing or observing any sample with a particular sample mean. Further down our journey, I'm going to show you how you can use the Central Limit Theorem and this formula in particular to approximate the mean of a population, mu, based on any sample taken from that population. Now, let's take a few moments to highlight some of the conditions of Central Limit Theorem. It turns out that if a population is normally distributed, the distribution of x bars will also be normal as well, regardless of the sample size. This implies that we could potentially have samples of size 20, 5, or even 2, and still have x bars that form a bell-shaped curve. On the other hand, if the distribution of a population is unknown, or simply if we have a population that's not normally distributed, we need to have samples of size at least 30 for the consequences of Central Limit Theorem to apply. Let's take a look at an example. Suppose a manufacturer of batteries claims that the lifetime of a certain type of battery has a population mean of 48 hours and population standard deviation of 7 hours. If we take a sample of size 50, what is the probability that the mean of our sample will be more than 50 hours? Before we solve this problem, notice that our sample size is 50, much more than the required 30. This means the consequences of Central Limit Theorem could be applied even though we don't know whether our population is normally distributed or not. So, to find the probability of our sample mean being bigger than 50, we use our standardization formula from Central Limit Theorem to find the probability of a z-score being greater than 2.02, which, using the standard normal table, we get an approximate probability of around 2.17%. Here is the Central Limit Theorem in simple words. Given any population, for example this one, if we repeatedly take samples of a specific size, say n, from this population, all sample means will follow the pattern that closely resembles the shape of the normal distribution.